Hello everyone and welcome to my talk. Today we'll be going over anomaly detection in adversarial networks as it pertains to high energy or particle physics. So briefly, here is an outline of the presentation. We'll be talking mostly about particle jets, their kinematics, and some of the ways that they're classified. So let's begin with a brief overview to see where the data is collected from. So our aim is to study jets, and jets are collimated flows of particles, hadrons, which in this case could be considered protons. By studying these jets, our hope is to find new physics beyond the standard model. And down here we have a brief figure depicting a typical experiment at the Large Hadron Collider. So this would be some experiment that aims to find physics beyond the standard model, where a jet substructure experiment is displayed from two protons colliding to create a resonance X. This resonance then decays into the lighter Y states, which could be W, Z, or Higgs bosons, or lighter beyond standard model particles. And here we have the transverse momentum P, which we'll define briefly. So let's look at some of the collision kinematics. It is helpful to adopt the coordinate system employed at the Large Hadron Collider. Thus, a particle's relativistic 3 momentum is given by p is equal to p x, y, and z. And here we have a diagram of how the experiment happens at the collider itself. We see that the z-axis is the direction where the beam is traveling by, and the transverse plane, in this case the y and x plane, are cutting the z-axis at cross sections. So we have the collision point, and we see that the phi angle is the azimuthal angle, and the theta angle is taken with respect to z. That's the polar angle. And here again, this is a typical experiment at the Atlas compact muon solenoid coordinate system. The azimuthal angle encircles the z-axis. So many experiments are symmetric about phi's, and so in this case we can focus solely on the transverse momentum pt, which is the square root of the px plus py, and we see that in this geometry it follows that the tangent of phi is equal to py over px, and the tangent of theta is equal to the transverse momentum magnitude over pz. Now, the rapidity w is yet another parameter that we can focus on because it's of importance, and is usually given in terms of the pseudo rapidity eta. Here, the rapidity w is usually given in terms of the relative velocity of the particle, where in the expression hyperbolic tangent of w is equal to v. And here w can be obtained from the Lorentz boost matrix in the usual form. If we have a transformation from a primed coordinate to an unprimed, we can just have this here. So we have the diagonal elements are hyperbolic cosines, and the off-diagonal elements are hyperbolic sines. And this is very similar to a rotation in Euclidean space, but it's a rotation in hyperbolic space. And this would just give you the coordinates between transformation for a boost between primed and unprimed coordinates. And from here it follows that at time equal to 0 the origin would just be, we can just solve for that and get the hyperbolic tangent of omega is equal to the particle's velocity, relative velocity. However, in as far as the rapidity itself is not a Lorentz invariant quantity, we are usually more concerned in the pseudo rapidity eta, and this is usually obtained for the highly relativistic case, so for highly relativistic particles. Since here we can substitute m equals 0, or in other case the particle's energy is entirely due to its momentum, and the mass is therefore negligible. And for this case, the rapidity is equal to another expression for the rapidity in terms of logarithms is the energy plus the momentum along the z direction, and on the numerator, denominator, we have E minus pz. So just doing a little manipulation of logarithms and signs here, we arrive at the next expression, which we can just put it in terms of the variables theta, and using just a simple definition of theta, we can just arrive at the definition that eta is equal to negative logarithm of tangent of theta over 2. So here we see a simple correspondence between the eta parameter and theta. We see that when eta is equal to 0, theta is 90, and as eta goes to infinity, theta is equal to 0. Okay, and here once again we have a more realistic view of the Atlas Diget event. So this is a proton-proton collision recorded by Atlas depicting a two-jet creation. The upper right-hand side, so this side here, contains a calorimeter clusters of transverse energies in the phi eta plane. So those are the parameters that we just discussed, and the z direction in this case is into the page. The x direction, so if we picture a ring, the x direction points towards the center of the ring of the particle collider. Next, we're going to be talking about jet classification. And we have basically different sources of jets that are present, and we need to be able to distinguish them from another. If, for example, the Y state is a W boson, it will decay into quarks, which will then recombine, or in other words, hadronize together for high energies, or in other words, for large boosts, and these are known as the signal jets. Opposed to this, alternately, we have background jets, which are quantum chromodynamic jets originating from quarks and gluons. And the process of differentiating between these two is called jet quark gluon tagging. So similarly, we may use flavor tagging to distinguish between heavy and light jet sources. Flavor tagging relies on reconstruction collision paths near the interaction point using high-resolution calorimeter sensors. Quark gluon tagging, on the other hand, relies on reconstruction from data taken during particle collisions at one location. So now let's go over generative adversarial networks and see how they can be used to classify data. Here we're training two neural networks to distinguish between signal and background jet sources, or in this case we can make it so that it distinguishes between pictures of cats. At the top we have a generator, so it's a neural network which can be thought of as the artist. It's a network trying to create pictures of cats that look real, and at the bottom we have a discriminator, which is the art critic, or in other words, a network that is examining the cat pictures to determine whether they're real or fake. And these are the two networks that we're going to be training. And here we have how this goes about. We see that in the first attempt, the generator creates a pattern, which then passes to the discriminator, which examines it and rejects it. After many attempts, it's starting to create something that resembles vaguely a cat picture, but however, the discriminator still rejects it. And even after many attempts, it creates an identical picture of a cat, which then the discriminator is unable to distinguish from a fake or a real picture. And at this point, the process ends, and this point would be when the discriminator is unable to distinguish between source and background jet production. So although we're talking about pictures of cats, the same concept can be applied to distinguish between two different sources of jets. And so here are some of the results that we've obtained from the repository found in the Explainable Artificial Intelligence for Machine Learning GitHub repository. So these histograms represent the particle counts at a certain polar angle theta. Here the blue graph represents the signal jet, while the orange is the background jet. We notice a Gaussian distribution for the signal at theta equals 0.2. Similar graphs depicting pz, the z component of the momentum along the line of the solenoid, were meant to be included, but are available in this project's repository. So the 20,000 labels were split evenly between signal and background jets. This means that 10,000 of these labels were signal events and 10,000 of them were background events. Out of the total 20,000 labels, there were a total of 18,508 and 18,520 correctly predicted base and regular lice models respectively. Similarly, there were a total of 8,532 and 9,976 correctly predicted base models for signal and background jets, respectively. We note that the code used in these graphs does not deal with anomaly detection, but is rather being used as a tool for understanding machine learning and neural networks as they pertain to particle physics. A more complete and working version of a similar code that deals with anomalies will be provided for the final. So here we go over a few end remarks. The types of network training that we would like to explore will be either supervised, weakly supervised, or unsupervised. The unsupervised training specifically optimizes a function giving some inputs. They learn directly from background sources and look for events with low momentum. Anomaly detection can be implemented once a generating adversarial network are trained in a similar fashion as was used to separate signal from background events. Care must be taken, however, as single events are insignificant. Only when we consider a statistical ensemble can an anomaly be verified. We can compare this to the flying elephant analogy. Here, if we see a flying elephant, for example, in our real world, we would know that it's not normal immediately. However, if someone was to ask us if it's normal for an X amount of elephants to be sitting and drinking water at a watering hole, we would have difficulty answering that question because we would need to know the total overall elephant population to see if today, in this particular day, there are more elephants than usual, or if perhaps the whole population is there at the watering hole, which would constitute as an anomaly. Lastly, we know that this project is far from complete. The main goal at this point remains to mold the generative adversarial network program into something that we can use for anomaly experiments. Thank you all so much for your time.